So then welcome to the series session number 2 of Virtual Fluids. Now we come to implementation details, number 1. So these are general implementation details. Later we'll talk about also some boundary conditions and grid refinement. So this is now much less in depth than we had in the theory 1, but it's important to understand if you want to deal with virtual fluids in order to see how it's actually done in the code. So in the code, we use something that's called in-place streaming. So now this is, there's a completely different topic now. We are not talking about equations now. We are talking about algorithms. Yeah, we do in-place streaming, and for this, let us briefly look again at the Lattice-Boltzmann equation, which I now, for practical reasons, write in a little bit different way than before, in a little bit more classical way. So we have the collision, Fij k after collision, and now I'll write this in a different way. I do the shifting of the velocities and the time steps that we had before in order to make it symmetric. Yeah, I can just shift this by half grid spacing, half time steps, so that I can actually write it down more in the way that is implemented in the code. And implemented in the code, it is, of course, at the lattice node and at the time is Fij k at the lattice node and the time plus some collision operator, and then we get the streaming as Fij k. Say this is the pre-collision at the next time step is then we do a full move, not a half move, the full move. Oh no, this is not an E, this is a C. Sorry. Cij k times delta t and to the next time step. So in the implementation, we don't do staggered. Yeah? We don't implement it staggered, but the equations are staggered anyway. So this is equal to Fij k after collision at this position x and the position t. So what you should anyway always do, even if you use different Lattice-Boltzmann codes, is you should combine streaming and collision, stream and collide. And there's two regular ways of doing this. There's what we call push scheme, where we write to the neighbor. So we can implement this like this: Fij k x plus Cij k times delta t and t plus delta t is equal to Fij k at the position x and t plus the collision operator in the same location. And this can be implemented by reading from an array B and writing this to an array A. And then after we've done this for everybody, we exchange A with B and B with A. Yeah, so this is how you can implement the Lattice-Boltzmann method. Then there is the opposite way that you can also use. This is the pull scheme. This is where you read from your neighbor. You read from the neighbor. This is Fij k x and t plus delta t. So now you're getting this from Fij, you're getting this from your neighbor. So this is x minus Cij k from the neighbor, delta t plus t. So once you write out, or you this is like pushing, or you're pulling this. This is the same. This is doing the same thing. So you just have to decide what you are doing, and this actually doesn't make that much difference. So you read from an array B, and you write to an array A, and after you have done this, you're exchanging A and B. Okay, I should draw this the same way, A and B. So you're rotating these two grids. So what you have here is you always have an input vector and you have an output vector, and everybody who works with finite differences or something like this is very familiar with this and probably thinks this is the way you have to do this all the time. However, in Lattice-Boltzmann there is something special, namely that this collision, or actually the complete update, is an operation that goes from RQ, so Q the number of velocities that you have, to RQ. So in finite differences, this is very different, right? So you usually you would update, say you have another Stokes solver with finite, with whatever, finite diff, or in any other way. So you would update, for example, one velocity component, and this velocity component would depend on the velocity of the previous time steps here and at your neighbors. So it's actually, so the information that goes in is more than what is going out, right? So we have velocity here, velocity neighbors, and maybe other velocities. Lattice-Boltzmann is special in that sense that the amount of information that goes in, that's all the populations on this lattice node, is the same as what is going out. And just from this, you notice that this only works if every information that you use is only used once. Yeah, in finite difference, information is reused. So there is a good use for caches. Actually, Lattice-Boltzmann kind of has this problem in modern computers, that there is no use for cache, because, I mean, not in the regular sense. It is used for reading cache lines together, yeah? But not in the regular sense, because we are not reusing data. Each population is used once and then can be discarded, which means it should always be possible to write directly from where you wrote, to write directly to where you read. But this can only be done if you do it in the correct way, because you don't want to overwrite your neighbors. Yeah? So this could be done by splitting this up between collision and streaming, and doing the streaming independently, but this is the most stupid thing you can do, because then you have to touch all the variables several times, right? And therefore you do it in a different way. So it is, for this reason, it is always possible to read and write from A to A. So this can be done in different ways. The way it is implemented in VirtualFluids is twofold. So VirtualFluids, you know that there's the GPU version and there's the CPU version. And for efficiency reasons, they use different data structures, because the data structure that is efficient on the GPU code is not the same that is efficient on the CPU code. And therefore, they work in different ways. So we'll talk about the GPU version now first, and then we'll talk briefly about how it's done in the CPU version. So the way it is done in the GPU version is called esoteric twist. You always have to give stupid. I mean, during lunch we should discuss how you actually do this dance. I have some idea how this is done. Esoteric twist. I'm going to explain this in one dimension in order to make it now simple. So there's a structure. So what we are using is structure of arrays. I always confuse these things, but I think we are using structure of arrays. So this is as in GPU version. I just now remember, since I didn't have time to prepare this because I took so much overtime, I wanted to show some pictures. Now I have to draw everything by hand because I could not pick them up. Okay, let me try it out. Yeah, so say we have 3 different arrays in this one-dimensional thing. DA, so data A, data B, and data C. Okay, so this is where we store our data. And in this data includes all the different populations. And now say we store them according to a coordinate x, say, and we want to pick out a certain node, say the node number n, and we pick out DC at this node number n, dB at this node, and then we do something strange. We put out dA at the node n plus 1. And now we distinguish between even and odd time steps. Even time step. So say we store f minus 1. We get f minus 1. We read this from dA at the position n plus 1. We get f0 from dB at the position n, and we get f1 at the position from DC at the position n. And this is what we do when we read our data. Now we read our data, then we do the collision, and then we write it back. So writing it back goes now like this. We have to store in dA n plus 1. So we can only use positions in our arrays from which we read, right? Yeah, because these are the ones that we do not need to keep. Now, what we write into this is not f minus 1, but we write f1 after the collision. So the one that previously moved in the other direction. In dB, at position n, we write f0, so this is just the same as before. And in DC, at position n, we write f minus 1 after the collision. And this is what we do in write. So then, this is what we do in an even time step. And then there's the odd time step. So there's odd time step. This is f minus 1 is read from DC. Now, you know, I changed the order. Now I have to read the opposite way. Yeah, so I read f minus 1, DC from n plus 1, and I read f0 from dB again at the position n, and f1 I read from dA n. So this is what we do in read, and then we have also the write DC n plus 1, I write f Yes. Do you see if I write F1 after collision, dB, and I write F0 after collision, and dA at the position N, I write F minus 1. So this is the right. So now what happens? What happens is that the one that has been moving to the left is always going one further left, and the other that was going right is doing one further right, and we're changing the direction all the time. So why are we doing this in this strange way? We're doing this in this strange way because we have these list-based data structures in the GPU code, meaning that the lattice nodes are not given in a big matrix, yeah, but we have some coordinate. So we have a lattice node, and each lattice node has an entrance of the different distributions going the different ways in the different arrays, yeah, and they can be completely unstructured. Maybe this is not important for people who are dealing with wind farms, because you can easily think that this is a box, yeah, for you. But if you have a complicated grid, like one that you get even in wind farms, if you do grid refinement, yeah, so then you have very complicated domains, and then you unroll this in these arrays, yeah. Then you need to know where your nodes actually are, and if you need to know where your neighbors are because you do the communications, then of course you have to store a lot of infrastructure here, yeah, because you have 26 neighbors. However, if you do this isotwist thing, you only ever are concerned with neighbors to one side of you. Yeah, so you don't need to go in the other direction. I mean, sometimes if you want to do something complicated more than moving particles around, yeah, then you still need this, okay? Then we were too clever again, yeah, but if you just do the fluid dynamics, you only need neighbors to one side. So now because I don't have the pictures here, I'm just drawing this here in 2 dimensions, because otherwise nobody will understand anything. Again, so if we had it in 1D, now we are storing in 2D. You could imagine it like this. This is the node for which we have the coordinates. We're storing the one that go into the positive neighbors in our node here. Then we store these things going here to the neighbor, to our north. Then we store these 2 here in the neighbor that is into our east, and to our northeast we store the one that's coming to the southwest. So this is what we do when we read, and then when we write it back, we write this one here, this one here, this one here, this one here, this here, this here, this here, and this here. So advantage is that access to neighbors only in positive direction. So the most complicated thing apparently is that we have to go to the northeast of this thing. But you can also think about this. So you need to know your neighbor in the north region, and you need to know the neighbor to your in your east direction. So then you know that the neighbor in the east direction knows the neighbor in its north direction. So what you actually have to store, you can actually reduce this to actually only one pointer in 2D, but we have not done this. So you have a pointer that goes in y direction, you have a pointer that goes in x direction, and here again you have a pointer that goes in y direction. So px pointer x and py pointer y. So this means this thing here has a low bookkeeping cost because we need to know only neighbors in the cardinal directions and also in one cardinal direction, not in the opposite direction. So low book for indirect addressing that we are using in the GPU version, indirect So what we need is we need 3 pointers in 3 dimensions, yeah, instead of 27, instead of 26. The other thing is because we only write where we read from. This is also completely thread safe. This means we don't need any particular order in which we execute this, which is especially good for the GPU, because on the GPU we don't actually know the order in which our lattice nodes are processed. Okay, right. So this is how it's done. How this is done on the GPU. Then we also have the CPU code or CPU module, which is a block code. So here we have a different data structure. Here, all the data is put into blocks, and these blocks are then connected together. So unfortunately, there is no way to do this this completely automatic streaming over block boundaries. So at the block boundaries, you actually have to copy data from one part to the other, which is also the idea because we want to distribute the blocks over many compute nodes. Yeah, so you anyway always have something to copy in between. But inside you can still use this, and we're using something similar that's not exactly the same, called this esoteric split. And because I don't have the pictures now on me, I will simplify this a little bit. So say we split our data. Now we are not using this. We are not using either a strict array of structure or structure of array configuration, but we do it a little bit differently. We split our data in 3 parts. Call this a split 0. In the split 0, for any block is an array where we have all the populations that do not move, F0, 0, 0. And they go from node 1 to node n, say, yeah? Then we have a split A. So the split A needs more data, 13 times more data, because we have stored together, and the idea with storing together is that the processor that is dealing with one lattice node should read as much data together as possible, right? So we do not like to distribute everything over different arrays, but we store now 13 of these populations together. Yeah, and these populations would be like F. They are now ordered like F1, 0, 0, F. What is it? No, not minus. F1, 0, 0, F 0, 1, 0, and so on. So 13 of this. So all of this is N1, and then comes N2. It is the same order. And then there is a split B where that has the same, this has the same ordering here, just in the opposite direction. So here will be F minus 1, 0, 0, and F 0 minus 1, 0, 0. And 13 of these populations, yeah. So I don't have the picture on me, which are they, I don't want to write the table down, which go one way, but they are arranged such that we maximize locality here. Yeah. So we have, unfortunately, this is not perfect. So you cannot. So there is only 7 of them can be read completely locally. Yeah, and the others have to be read somehow distributed. But we store 13 of them together in this one direction and in the opposite direction. And then what we do, we read from split A, and then we write opposite to split B. Yeah. So basically, we're doing the same esoteric twist, just with a different data structure. So the idea here is read and write as local as possible. Okay. So now I would come to the numeric part. So what if, I mean, we are already in lunchtime, right?
Yeah, but it's fine.
No, because we could make now the logical break.
Yeah, then that's fine.
Then we make a break here and start 10 minutes earlier later, right?
Yeah, I guess half an hour lunch is also fine, right?
Yeah.
Then you have a bit more time.
Okay. More lunch for thought. Yeah, food for thought. Okay. I'll stop the recording and we stitch this together later because I don't